Okay, good morning everybody, good evening, whatever time it is there. I am coming at you from Missoula, Montana, and we are covering the curriculum for Sri Lanka PV. And so far we have covered NRGY 101, NRGY 102, and we have started into NRGY 243. And what we're calling this one is the Sri Lanka PV Curriculum Review 4. And what you'll see in this quiz is that there are several concepts. We kind of go back into a few things from NRGY 101, which was mainly conventional energy, and then we go into 102, which is renewables, but there's also a lot of things in this exam that cover specifics of photovoltaic systems. So let's go ahead and get started. I'm not going to spend any time on question number 1 because we already did that briefly a couple days ago on May 8th, 2017. Okay, so let's go ahead and look at this next one. So a PV system, this is number 2, a PV system that operates in parallel with and is connected to the electricity grid is called what? Well, in this case, we're looking at a PV system that is tied to the grid. So obviously the key word here is connected to the utility grid. It's not standalone. I could sketch up a little diagram for you here. A second to get my pad rolling. What I figured I'd do today is just show a few pictures. There's so many great images out there, and this is one of the simplest ways to look at the system. So here's your photovoltaic system. This is all DC, so it goes into a combiner box. Of course, it is earth grounded, so you've got a relative charge between the panel and where you're standing. You've got an AC converter typically, and this will go to a panel and then off to the grid. So the answer we're looking for, and they're just this is mainly just language. So utility interactive, meaning that your PV system is working with the utility or with the grid. It's also grid connected, it's interactive, and it's grid tied. So the answer there is all of the above. Okay, next system. A battery is a group of batteries connected together with series and parallel connections to provide a specific voltage and capacity. So the answer here is a battery bank. I'm going to go out and take a look at that for you, and I'll identify. So in this case, a battery array, I mean, you might call it that, but that's not the proper term. I'll show you what a bank is, and I'll show you what a cell is. Okay, so again, I have come up with a pretty cool little graphic. This is much faster than using my old pad here, and what these guys are showing are 4 batteries in series, so you would consider this to be a battery bank. This is a battery bank with 4 batteries. The thing to keep in mind here is each battery has 12 volts, 12 volts, 12 volts, 12 volts. Since they're in series, so positive, negative, positive, negative, positive, negative, positive, negative, all 4 12s equals 48. And that's very simple math. So let's just take a look at this. So batteries in series, get this pad rolling in a second. Okay, so here's a single battery. There's a battery. And the typical voltage is 12 volts. And frequently what you'll see are several cells in here. So you might have 1, 2, 3, 4, 5, 6. Each one of these is going to be a 2-volt cell, and they're also in series, connected together. And if we take several of these, see if I can grab this guy. Okay, what I'm showing here, so I just copied and pasted this. And so if we go from our big negative down here to our big positive here, we've got 12 volts at each one. We jump her over, jump her over, jump her over, jump her over, and so the total voltage, the voltage total, equals V1 plus V2 plus V3 plus V4. This is V1, this is V2, this is V3, this is V4. All of those voltages are 12 plus 12 plus 12 plus 12 equals 48 volts. So that's for the series connection. Now if we look at these batteries in parallel instead, the voltage you can see across each one, all these are at the same voltage. This line is also in the same voltage, so the most you're ever going to get is 12 volts. Now you'll notice that in this case the amp hours are different. Here the amp hours are greater, and let's look at the implications of that. So that's our voltage. Now if we look at our total energy, okay, so now I've gone and just put these in parallel. So to take a look at that, each one of these are jumpered together, like so, like so, like so, like so. So we'll have one big minus over here. It's the same minus down here. On this side we'll jumper all the positives together. We'll have one big positive up here, another big positive here, and again you could call this 0 volts, and this is 12 volts. So for series, energy, if we go back to our, that's always volts times amps times hours. Again, this is going to give us watt hours, because remember, volts times amps is watts. Let's take a look back at that period. So we're going to do 50 amp hours times 48 volts. So 48 volts times 50 amp hours equals, run that through our buddy here, the calculator, 48 times 50 equals 2400. 2400. And we'll just put this in watt hours. And if we go back to this guy, 200 times 12. 200 amp hours times 12, so this is for parallel. Energy equals 12 volts times 200 amp hours equals, and I think we get the same number. Let's just take a look. 12 times 200 equals, there we go, 2400 watt hours. 2400 watt hours. In both cases, these both equal 2.4 kilowatt hours. So there you go. In both cases, the amount of energy is the same. It's just that this guy is going to give you more current. This guy is going to give you more voltage in general. Now if we go ahead and double it, So what we've done, we've got a series in parallel with another set of series. You can see that it doubles. So series plus parallel. What we're looking at is 48 volts times 100 amp hours equals 4,800 watt hours equals 4.8 kilowatt hours. So larger. Okay, so that's really the fundamentals of putting batteries together, series parallel, and calculating the total amount of energy. Okay, there we go. So let's head on to the next question here. So now we saw this was a battery bank, different ways to put them together. I showed you what a cell is. It's always the lower voltage. And there we go. Okay, next one. PV modules, and this is fairly straightforward, produce direct current, and that's true in every single case. At least on the low time scale, you always have a positive and a negative on a PV module, and we can get into more of the science of that, but that's enough really to know for now. Okay, charge controller. Let's take a look at the charge controller. Again, I'll go out to the interwebs for that. Okay, so here's a shot. Here's a shot of a PV array, and thank you, Aladdin Solar, for allowing us to use this. We'll at least acknowledge you, and we'll ask for permission. Where are you? You're in Excelsior, Minnesota. Titles and author C. Pickard. Thank you very much, C. Pickard. Okay, so here is a PV array, photovoltaic array. The output goes into a DC, so again, direct current disconnect. Here's the charge controller we're looking for. And so you can see straight from the DC disconnect through the charge controller goes right into your battery bank. So what you can see is if you're going to work on this bank, you can disconnect it here. If you just want to disconnect the array, we'll disconnect it here. If you're out in the middle of the woods, for example, you would just sort of have this connection. There's really you can see there's no connection to the grid. This is sort of your grid, if you will. This backup generator might be something that's a thermal plant, burning some type of combustion. Here is the inverter that takes you to the AC connect and your AC loads. And if you had DC circuits, and I think we're going to see a lot more of these as we move out into the future. There's some nice standards coming out for doing low voltage in homes. So charge controller is what's going on to make sure that these batteries stay at 12 volts of charge and do not overcharge. So that's what we're trying to prevent. We do not want the battery to overcharge. It takes a look and sees what the battery bank and output are. You might have a dump load, something, so if there's too much energy, coming in from the PV, you might send that out to a dump load like a heater, like an air conditioner, like some other type of energy storage. All right. Here's the next one. The question is, what type of switch allows an electrical system to be switched from a primary power source to an alternate power source to keep the critical loads operating? Let's go ahead and take a look at that one. All right, so this is kind of a simple schematic, but here we can see right over here is a transfer switch. So again, up top, sorry it's covered, but that's the PV array right there. There's the charge controller we talked about before that goes down to the batteries. This is a voltage controlled switch that will switch on and off depending on what type of voltage is there, which controls the relay. So the relay will allow the inverter to come on or off. So this the DC obviously is coming from the battery, and the AC is going out to the appliances. Now the transfer switch can basically say, hey, I want all of my electricity from my system, from my photovoltaic system, or it can go and say, hey, I want my electricity to come from the grid. So it's sort of an either-or thing to keep your AC appliances running. So that's the meaning of the transfer switch, transferring from the renewable system to the grid system, or vice versa. All right. Here's a neat one. So blank stores energy in an electrical field developed by two oppositely charged parallel conductive plates with a dielectric. All right, so the answer here is capacitor. And I love talking about capacitors, and I'll show you why here in a second. Okay, I was out looking for kind of a neat little video on this, but here are the three fundamental components in any electrical system. So this is R. This is the resistance of a circuit. So you can think of R as being the filament in a light bulb. You can think of it as being the work done by a motor. You can think of it as even this computer has a lot of resistors in it. This thing L, this is an inductor, and these are actually the windings in a motor. So you can see these little coils here. So if we go out, let's try to find a shot of a motor. So again, I just went out and checked out a motor. So these are this is the copper winding inside a motor, and that's really what we're looking at right here. So this is an inductor, and then what we're after in this problem is the capacitor. And notice right here how in the capacitor there's no way really for the electron to jump across. They bounce in and bounce off of this plate. So you can sort of think of this as a springboard or a trampoline, something you're just bouncing back and forth. Same thing over here. The electron never really passes through the capacitor, but think of this little sine wave as pushing the electrons back and forth, sort of sloshing around. Oh, and so here we go. This is a picture of real capacitors. So you always see there's two sides to it, and inside the capacitor, and I'm going to try to see if I can find a neat shot of that. All right, what I'm showing in this picture is that inside the capacitor there are two big plates together, and so there's always a gap between them. So there's always a dielectric material where no electricity can pass, but all of the all the electrons are stored on the two plates that are separated. Okay, so that's the answer to this guy. The other thing to keep in mind is that capacitors can charge very quickly, whereas batteries take a longer time. Okay, so here's the next one. Choose all of the following balance of system components. And the balance of system components is just going back to where we were previously. So I couldn't really find a very good image for that, but this is just showing that there are a lot of different components that go into the balance of the system. And that's an example for wind. You can also sort of look at this as kind of a interesting little shot. This is just showing that the DC generation, how much DC you have in your solar array, needs to be comparable to whatever your typically AC load is. So they're just showing the balance of system, that all of the energy generated from the PV array equals what is consumed. Okay, so that's the way to think about the balance of system. So the fans, that's a load. The lights are a load. Pumps are a load. The racks hold the PV panels in place. The junction box, we've seen a lot of those already. The breakers, we've seen those in our diagrams. We've also seen the charge controllers. So all of the above is the balance of systems component. It means everything in the system. All right, so this guy, a blank, is a device that converts DC power from one voltage to another voltage. So in this case, didn't say anything about AC. So really all we're doing here, we're going from one DC voltage to another. And that could be going from 12 to 48, for example, e.g. 12 volts to 48 volts. Another way you could write that is volts DC to 48 volts DC. So that's a DC-DC converter. Okay, this one's kind of fun. What's the most common type of energy storage for PV systems? Well, not typically a flywheel, but those are pretty cool. Not typically a supercapacitor, which are great. Not typically pumped water, although those are happening. Not typically compressed air, but those are coming online as well. Fuel cells are there, not quite as common. So the battery is the most common type of energy storage, and that's what we usually focus on. As it's a well-known, usually compact, doesn't take a lot of extra technology, and sort of easy to understand and easy to maintain. All right, so how about this one? A blank turbine is a device that compresses and burns a fuel-air mixture which expands and spins a turbine. So an engine is just a generic name. It's not exactly incorrect, but it's not the best answer. A wind turbine does not burn any fuel, so that's why a wind turbine is not correct. And a power turbine is sort of meaningless, so the answer is a gas turbine. And let's just take a look at one of those. Let's take a look at some images. And these really are fantastic devices. I mean, if you sort of look at one of these guys, this is how big some of these can get. And you can see there's a worker standing next to it. And so throughout this, you have combustion taking place. This entire thing spins, of course, making electricity. And these gas turbines are becoming more prevalent as we move away from oil, as we move away from coal. And just while I'm thinking about it, let me take you out here really quick. This is a quiz that I'm writing up, and this is the grid profile for energy in Sri Lanka. So let me see if I can make this a little bit bigger. Okay, there we go. So hydropower is a significant portion or fraction of the grid in Sri Lanka. You can also see that a lot of the energy comes from oil. That's what these bars are. You can also see that coal has been coming online recently. Here's the coal portion. Other renewables, fairly modest, but we're seeing growth. And I think what we can also see is that in general, the demand for oil has begun to diminish. So I think this will soon be gone. I'm a little surprised to see this much coal, and I'm also surprised to see no gas turbines in Sri Lanka, because these are becoming more prevalent as natural gas is coming online. Okay, so that's that question. So that's what a gas turbine is. All right. Here's the next one. A blank is a device that converts mechanical energy into electricity by means of electromagnetic induction. So in this case, the answer is a generator, and there are several types of generators. I'll take you out here for a little bit. Wind turbine generator. Let's just go and look at some images for wind turbine generator. Okay. Yeah, this is a pretty good one out here. So let's just take a look at this image. So the question said we're going from mechanical energy, and that's what this is. This guy is mechanical energy. They're showing that it can rotate a little bit. You have a gearbox, and back here, this is the generator. So you can think of it basically as a motor operating in reverse. The mechanical energy comes in here, the generator spins, and out goes the electricity. So, and they don't show a good shot of it, but sure enough, down this tower, which we can see is 15, the electricity flows down out of the generator. Okay. An inverter, as we know, an inverter is always going to convert DC to AC voltage, and we've seen that several times. Let's see if I can take you back to it. Yeah, and here's the inverter. We've seen that before. So the inverter always goes from DC to AC power. Very important in a grid-tied system, or if you want to run an AC load. All right, so question 14. Which two types of components are most common in standalone and utility? Well, you always have to have the PV modules, and typically you're going to have an inverter. Rarely will you have a system that is just DC. This is always to get you to AC power, alternating current power, motors, fans, things like that. And I've even seen when we interact in your classroom, I can see in the back behind you, you typically have a fan going to keep the room cool. So the AC that's an AC fan, almost certainly that's running that. So you need to go from your DC to your AC with the inverter. All right, 15. Generator sizing for off-grid homes is based on, and what we're looking at is the minimum charge rate with the inverter charger. And let me take a quick peek at that and get right back to you. Okay, so what I've gone out and found a neat little chart here. So a C5, this is basically charge 5, means that you can run for 5 hours. This is C10, this is C20, and what you can see that in each case, the available energy, it's a little bit longer. It's a little bit longer if you go out to a longer period, not by much, but here's your C20, meaning that you can run for 20 hours. 20 hours. So if the supply is properly designed, it will handle the startup surge of all loads. So if you all of a sudden turn on everything, so achieving a minimum C20 battery charge rate means if you turn on everything for your off-grid home, the battery bank is large enough to accommodate this, and the idea is that you could actually run for 20 hours with it. So it's not necessarily the number of appliances, it's how big they are. Startup surge is important for a well pump. This is so you have water, but in this case you're looking for all of the loads. So you want a battery bank that has enough capacity so it can run for a long time, but also it can take all of the loads to run. So 18.5 amps. This is well, it's only one circuit, but remember you're going to run that for a solid 20 hours, and here's your 2.2 kilowatt hours. That's the amount of energy in that system. All right, so that's what the C20 rating means. All right, I think I've got one more page, and then we'll be done for the day. Engine generators in residential grid-tie battery systems, and we just saw this a second ago. So extend them indefinitely. Well, I guess this is true as long as the fuel runs out, and it just says so if your battery bank goes down, or if your solar panel goes down. Let's go back and take a peek at that. This was that good image we saw before. So if the panel goes down, the batteries go down, this is the backup generator that can run the system as long as you keep putting fuel in it. All right. And then what's the next one? It says, which is not a main role of an engine generator in an off-grid residential PV system. So what we're saying here, there's no need to rest a battery. The batteries like to be charged and discharged. So no need to rest a battery. So it is used, of course, if your batteries go down, you need backup charging. They can also equalize the batteries. It's important that all of the batteries be at the same voltage, and if you need extra capacity, then the generator can come on. Okay, and so as we saw before, there is no need to rest a battery. All right, now the next question, when a typical 120, 240 generator that's not capable of a full output at 120 volts is paired with a 120 inverter, what's the problem? Well, of course we know that the generator is oversized. The inverter will not accept the generator output. The load on the generator is unbalanced. That's the key word here, because we're two different voltages. And the generator is only capable of half its rated output. Well, that's not the case. So, again, if the 120 is not capable, that's the key word there, is not capable of full output, this is what happens. B and C. B and C. The inverter will not accept any input outside of its voltage AC input. It will also create an unbalanced load on the generator if it's trying to run 120 volt AC when not putting out 120. Okay, so it's very important that you have matched voltages. All right, finally, the manufacturer-rated generator output, A, should be derated for high elevation and ambient temperatures. And so what we're looking at is generator output should be derated for high elevation and high ambient temperatures. Now, this is true for solar panels, and it's also true for generators. So if you get over 3,000 feet, there's just less oxygen. If you get over 90 degrees, and so if you're at less oxygen, the generator does not run as smoothly. There's just not as much oxygen in the air. And if you get over 90 degrees Fahrenheit, let's just convert that to Celsius. So 90 F to C, 90 F to C, 32 degrees Celsius, you know, pretty warm, getting up there, 32 degrees Celsius. If that happens, then the generator is not as efficient. So it has to be derated, meaning that it does not operate as efficiently. Okay, well, that's what I got for today. That's kind of a broad overview of on-grid, off-grid systems, some of the components, some of the language that you're going to be using in your upcoming build. And thanks a lot for your attention, and we'll see you, I think, on Friday. So give me a shout on the WhatsApp app, and we'll talk more on Friday as we get into our lab. So thanks, everybody. Take care. Bye-bye.